Hello, this is Adam Pawson, welcoming you to this Bite-Sized Bio webinar. Today's presentation is titled Errors and Misconduct in Biomedical Research and is being presented by Dr. Elisabeth Bik from Harbers Bik LLC. Elisabeth Bik, PhD, is a Dutch-American microbiologist who has worked for 15 years at Stanford University and 2 years in industry. Since 2019, she is a scientific integrity volunteer and consultant who scans the biomedical literature for images and other data of concern and has reported over 7,000 scientific papers. For her work in science communication and exposing research misconduct, she received the 2021 John Maddox Prize. As always, we will have a question and answer session after the presentation, so please type any questions that you have into the questions box, which appears on the top right panel of your screen, and I'll put them to Elisabeth at the end. Details of how to access the on-demand recording of this webinar will be sent to you by email shortly. So now over to you, Elisabeth, for the presentation.
Good morning from San Francisco. This is Elisabeth. So it's very early for me, and I apologize. And I just had a cold, so I hope you can still hear me fine. So today I'm going to talk about errors and misconduct in biomedical research. And so before I start my talk, I want to make sure that I have all my financial disclosures out of the way, because sometimes I will criticize another paper for not disclosing their financial income. And so I, of course, need to make sure I do this myself. So I am not employed. I don't work for a university or a company. I work for myself. I have a consulting, small little company for myself. And with that, I receive consulting fees and speakers fees to give talks at universities. And I sometimes also work for publishers to investigate cases of suspicions of misconduct. I also have a Patreon account, which is a crowdfunding site. So I get a decent amount of income through that. So I'm very grateful for my donors who support my work. I have worked for a fraudulent company called Ubiome, and that the company is now bankrupt, doesn't exist anymore. The founders have been indicted with insurance fraud and all kinds of other nasty things, but none of the employees have been accused of that. So I do have 4 patents from that time, but I don't think they're worth much money now that the company is no longer there. And so the work that I do focuses on images, as you can see on this slide, images that can be duplicated or completely wrong in scientific papers. And why do I care about scientific papers? Because you might think that once a paper has been published, once a paper has been peer reviewed and gone through all that process of criticizing it, and it's being published, why do we care about it? Is it set in stone once it's peer reviewed? And the answer is it's not set in stone, but we can still find errors and suspicions of misconduct in it. But for me, publications are important because they're the foundations of science. They're how we scientists communicate with each other. But I also have a very strong personal belief that science is about finding the truth. And when we're scientists, we're trying to discover what the truth is, and we share that with others through publications. And then we hope that other people share their publications with us, because this is the way we do science. We do not do science just by ourselves. We work in teams, but most importantly, we build our work on the work of others. We don't, yeah, we're not a unique entity in the world of science. We always build our work on people's work that has been done before us. And so I see science and science publications as bricks in the wall of science, onto which we layer new layers of bricks every time we publish a new study. So we tend as scientists also to believe and to trust each other, but unfortunately, science is not immune to fraud. So if one of those publications, one of those bricks is not good, that means that part of that wall, all the other publications that rely on that first publication, are perhaps not on stable ground. And so part of the wall could be tumbling down. And so I care about scientific publications because I feel if I would discover an error or if I would suspect misconduct in a paper, I need to say that because other people might waste a lot of time trying to replicate those results and they might not know that there's a problem in the paper. And so, if you think about specifically science misconduct, there are three types of science misconduct. There can be many things, many parts of a paper can be wrong, but not all of that is misconduct. A lot of things that we see in science that is not correct could just be errors. There are many questionable research practices, shown here on the left, but real science misconduct, at least in most countries, is defined as one of three things: plagiarism, falsification, and fabrication, in which plagiarism is copying somebody else's texts or ideas without giving credit. Falsification is where a person changes some of the results to perhaps better fit a hypothesis. Excuse me. Um, while fabrication is where a person completely makes up results, so doesn't even do an experiment. So those would all qualify under science misconduct. But I also want to point out that behind every case of misconduct, there is potentially a sad story. Because why would a person do misconduct? Yeah, we all feel the pressure to publish, but why would a scientist really go that far to deviate from finding the truth and actually reporting or changing results? I'm sorry. So I want to point out that on most papers, there's multiple authors. So this is actually my first paper that I got retracted because I found a big um, suspicion of misconduct in it. There are multiple authors on this paper, and we do not really know who is responsible for findings of errors or misconduct in a paper. It could be the first author, or it could be the last, or it could be all of them. Now, let me drink some tea, see if I can fix this problem. It's hard to know who is responsible, and you could argue that the first author, perhaps who made a figure, is responsible for perhaps photoshopping an image. But in the end, the last author, the senior author, is responsible for the whole integrity of the whole work. But very often we'll see that the last author would um, blame the first author for doing the misconduct. In the end, all the authors on a paper will be damaged if a paper is retracted for suspicion of misconduct. And not just perhaps the author, but all other people working in that lab or all other people working in that institution. But you can think of several scenarios where people would do misconduct. And the scenario I usually give is that of a foreign student working in a lab in the US. So they came to the US in the hopes of working at a big name university, but they're on a visa. If you're on a visa, that means that if you are fired, that you have to leave the US and go back to your home country within a couple of weeks. It's a very short period. So if you are perhaps working for a very demanding, perhaps a bullying professor who perhaps tells you, oh, if you don't give me those results that I had hoped for, I will find another postdoc who can do the work. I think you could interpret that, rightfully so, as a threat to be fired. And I think in situations like that, and it's just an example to give you hopefully a little bit more sympathy for why people do it, um, it's that you want to please the professor. You want to get out of that lab with a publication. And so you're very afraid to get fired. And you might just want to please the professor and give them the results that they want. And in the end, the senior author, the professor, is responsible for the, the atmosphere in the lab. They should create this atmosphere of supervision, of mentoring, and of work making sure that the results are good and solid. And so I do want to point out again, I'm not going to point fingers. We can have fun with the papers, but I do not want to point out who did it. So I'm not going to show any author names on the next couple of slides. But I also want to point out that we can separate the problems in a paper to the question of who has done it. That those are two separate questions, and we can look at a paper and potentially see a problem with it, but who has done it, who was ultimately responsible for it, that is a very difficult question to answer, and that has to be done by the institutions, and it needs a lot more material than just staring at a paper, because the answer is not going to be there. And so the parts of a paper that I would look at look like this. I look at figures in scientific papers, specifically biomedical papers, because that's my background. And I would find photos that could be either line graphs, as you can see here on the left, or photos, as you can see on the right. Now, I mainly focus on photos because in photos there's a lot of details, and we can examine these photos of tissues, of mice, of gels or blots of cells, and we could perhaps spot potential duplications in these or potential photoshopping. In line graphs, that would be much harder to look at, and yeah, who knows if the line graphs on the left are real or not. I know I made two of them, so I know two of them are real, but it's much easier to catch misconducting photos than it is in line graphs. Here are three examples of inappropriate image duplications in photos that I have found in the past. And so there's three different categories. Starting on the left, we have a simple duplication. You see two sets of photos that appear to look identical. You see a lot of panels here that are all slightly different, but two sets are identical. It's the exact same photo that was used twice to represent different experiments. And this could be an honest error. You can imagine a person having done a lot of experiments and taking lots of photos and not really keeping good track of their photos. So it's sloppy, but it could be an honest error. It's not necessarily misconduct. In the middle, there's an example where you see four different photos of cells being treated with different amounts of radiation. Two of these photos here on the top overlap, and I've marked that area with a green box. And the two photos on the right also overlap, which I've marked with a blue box. So three of the photos were taken from the same specimen. The sample was moved under the microscope a little bit, and a new photo was taken. But it is the same sample. So instead of looking at four different experiments, at best, we're only looking at two. This could also involve this type of repositioning, could also be mirroring or shifting or stretching or flipping or rotation, things like that. So that would be a repositioned image duplication. And on the right, you see an example of an image duplication in which parts of the photo themselves appear to have been duplicated. So you see four Western blots, A through D, and in Western blot A, you can see that lane 1 and 3 appear to look the same. There's lots of little dots that you can look at, and it appears that this photo has been photoshopped. And here in the bottom panel, you also see three lanes that look remarkably similar. Now, this type 3 duplication, in which parts of the photo itself have been changed, is very likely to have been done deliberately with the intention to mislead the reader. So the repositioned one, type 2, is sort of falls in the middle. It could be done intentionally, it could be done by an honest error. It's not always easy to know, but these categories sort of help a person to try to determine if it was done intentionally or not. And here are a couple of other papers or YouTube videos that you can watch that also address these duplications and image alterations that are not appropriate. Now, I have put a couple of slides in this presentation where you can test your own ability to spot these duplications. So here you can see 7 panels, and as you can see from the labels, these are all supposed to be different photos, different experiments. So they're cells, and the photo was taken under a microscope, but 2 of these panels are identical. Can you spot the 2 that are identical? Well, I'll take another sip of my tea. And this is a very easy one. I hope most people have found the answer. There's two panels. The first and the third panel are identical, and they should not be. And so this is a type 1 duplication. I do want to point out again, this is very likely to have been done by an honest error. And some people online actually had the correct answer, A and C. And so I reported this to the journal in 2015, but the journal never took any action, unfortunately. And yeah, this is not, a huge error. This is not really breaking the conclusions of the paper by any means, but yeah, it's a little thing that could have been corrected. But the authors or the journal or both of them decided to not take any action. Here's another example of a type 2 duplication. So here is a bunch of panels, again, of cells grown, and the photo was taken under a microscope. And as you can see, there's two different cell lines, and there's a bunch of different treatments. So none of these photos should be the same, but there's actually several photos that overlap. So this is a type 2 duplication. The sample was moved under the microscope, and there's a couple of overlaps here. So I'll leave this up for a couple of seconds and see if you can spot one or two overlaps. And there's lots of them actually. So I'll show the answer. So there's lots of overlapping images here. And yeah, if it was just one set of overlaps, I would say, yeah, that's an honest error, sloppy, but not really any intention to mislead. But I think when you have this many photos that overlap, you have to sort of question why the authors did that. I mean, if you had a student that would produce so many overlaps, you would not think that they should be doing a career in science, because you have to know at the end of the day which sample is what and which photo belonged to which experiment. And the journal agreed with me, so I reported this in 2015, and it got retracted. But it was several years later, in 2019, that it got retracted. You can wonder why it took so long. Sometimes these type 2 duplications are a little bit harder to spot. So this is one that I found with, I believe I found this with the help of software, because this one, you can sort of see that some of these samples look very similar, but to really spot an overlap is actually quite hard. And in this case, the overlap is between J and K, and it involves a 90-degree rotation. So when it involves a rotation, these things are even harder to spot. So for that, you might need software, especially if the two panels are in different figures or even in different papers. But most of the examples I will be showing today I found by eye. Here's an example of a type 3 duplication. So here's a photo of a southern blot in which you can see several bands, several lanes, several smears. And the longer you look, the more repetitive areas you might find. So there's lots of duplicated areas in this paper. And this is quite concerning. This is a type 3 duplication, very likely to have been done with the intention to mislead. I reported this almost a year ago to the journal, but it hasn't been addressed at all. Sometimes these type 3 duplications can get quite elaborate, and it is actually sort of fun to try to mark them all. And sometimes I find part of this by software, and you look at them by eye and you start to find more and more and more. And yeah, so in this case, you can see that samples have extensive areas where with duplicated regions, and it's not clear why. Maybe if one of them is in a corner, it could be to hide, for example, a scale bar. But if there's multiple areas of especially here and here, when you see these multiple areas of overlap, I'm not sure what they were trying to hide, but it's not the result as they were initially found in the lab. And here's an example of Western blot art where many parts of these images appear to have been duplicated. Again, not quite sure, but you can see in some cases there is a band of interest at a particular height, and then there's some duplicated area. So maybe they were trying to hide some bands that they did not want to show, or maybe it was just a little spot or stain. But yeah, it's not good, and I reported this online. This is from a lab in LA, actually. I have found sometimes these parts, these duplicated parts in graphs. So here's an example of NMR spectrum where parts of the noise has been repeated, perhaps to hide some of the peaks that perhaps showed that the compound wasn't as pure as the authors had wanted it to be. And perhaps they were trying to hide some of the peaks by slapping over an area of the noise from. But yeah, there's lots of repetitive elements here, and this paper got retracted pretty quick, within a year. Then there can be all kinds of other problems that are not in figure. So once you start doing this, your eye might fall on other parts of a paper too. And so here's a paper in which you see a table, you see lots of different measurements, and you might not at first glance spot anything suspicious. There's no duplications here. You see all kinds of measurements, and the measurements are given as the mean value, an average of several mice or rats in this case. So a mean plus or minus a standard deviation. But if you look carefully, you might spot that the standard deviation always seems to be the same percentage as the mean. And so I was looking at it, well, that always seems to be, there's almost no variation. If you take the mean and then you take the standard deviation and you would plot it, and as the percentage, how would that look like? And so I plotted it, and it turned out that all the standard deviations were 6.3% of the mean. And so it seems that they just applied a formula. Maybe they did one measurement and then they had that value, and then they just multiplied that by 6%, and then they used that as the standard deviation. But you would expect the standard deviation to be a much wider range, to vary maybe up to 20% or so, because in biology, you usually don't have very small standard deviations. But this was very suspicious, and it appears that this was fabricated. But unfortunately, the journal never took any action. So I have done a lot of scanning of papers to answer the question, how often would you find these image duplications? So not looking at tables like the last examples, but focusing on images and focusing on photos in particular. So I scanned 20,000 papers spanning a period of 20 years by eye. This was done before I had access to all kinds of software to help me with that. And I made sure to include several different journals from several different publishers. And my two co-authors, Arturo Casadevall and Frederick Feng, both had to agree with my findings. So if one of them or both of them said, well, we don't think this is an inappropriate image duplication, then I could not count it. These were all duplications within the papers. And most of these papers were in the molecular biology field. So they should contain at least one photo of a Western blot or a gel or something like that. In that set of photos, I found 800 papers that contained these duplicated figures. So that is 4% of the set. And we estimated that about half of these, so 2% of the set, had duplications that might have been done intentionally, with intention to mislead the reader. So the question then was, well, does that mean that 2% of all papers contains misconduct? Is that 2%, can you apply that over all papers? These were, again, papers with photos of blots or microscopy photos, mainly in the molecular biology field. But can you extend that to saying that 2% of all papers contains misconduct? And of course, that's a hard to answer question. Excuse me. Because there's many ways of misconduct that you cannot spot by looking at a photo. we could spot a duplication, for example, an overlap between two images. But imagine that if you move your sample a little bit farther under the microscope, there would not be an overlap for me to find. And so, yeah, in that way, I would not be able to catch a problem in that paper. Or if you uh, just had some believable values in a table or in a line graph, I would also not be able to look at that and have any suspicions of fraud. And so the real percentage of misconduct has to be much higher than 2%. Yes, there could be honest errors in papers, but the real percentage of misconduct has to be higher than 2%. Maybe it's 5% or 10%. And again, we don't really know. And maybe it does vary per field. Again, we can catch these things when it's in photos, but a lot of scientific papers do not contain any photos. They might just contain one line graph or a table or an ordination plot or so. But you would never know if there was fraud unless you were sitting next to that person in the lab and carefully recording what they were measuring versus what they had published. And that is, of course, impossible. We cannot all be watching other people what they do. We sort of still rely on each other and have to trust other people. But it is, yeah, I think it's a scary thought to think that 5 or perhaps even 10% of papers could contain misconduct. That's a very scary thought. The absolute numbers have to be staggering. But what is also frustrating is the lack, or at least the slow speed at which scientific papers and journals respond. So I reported all of these papers to the journals, and this initial set of 800 papers that I found, I reported to the journals around 2015. But after waiting 5 years, so around 2020, 2/3 of these papers had not been corrected or retracted. That's this big blue chunk here in the pie. 2/3 there was no action taken. 1/3 had been either corrected, here in yellow. Sorry, my microphone falls out. Had been either corrected, here shown here in yellow, or retracted, shown here in red. And there's a tiny sliver of expression of concern which is barely visible. So that is sad. Why is only 1/3 corrected or retracted after 5 years? And there could be many reasons. Maybe journals were overwhelmed. I sent them an email saying, "Here are 100 papers from your journal with problems." Or they had no idea what to do, or they just didn't believe that I was seeing these things. Maybe the authors didn't respond. So it could be all kinds of reasons, but it is a sad state of affairs that we tend to think that science is correcting, but it doesn't seem to be the way, because if I report all these problems, there was no action taken in the majority of the cases. By now, of course, I've found many more papers. So I found around 7,000 papers and reported around 2,800 to the journals and institutions. And most of these cases I reported online on a website called papier.com, because I want to alert readers that there's a potential problem. And if you do it the official professional way by alerting to journals and hoping for a response, as I have found out, the response is almost not there. And so for me, the best way to warn other people that there might be a potential problem is to report these things online. And so I use a website called papier.com, which calls themselves the Online Journal Club. And you can install a plugin that will work with your browser. And if you do a literature search and you have your plugin installed, you will see these green banners in your literature search when it picks up a DOI, a unique identifier of a paper that has been reported on Papier. And so you can use this website to comment on a paper. And you can also use it to just see if a particular paper or a particular author has been commented on. And those search results might be quite interesting. I'm using, as I already mentioned in a couple of slides earlier, I'm starting to use software. So most of all the 800 papers that I found in my initial search in 2015, which were reported in 2016, those I had all found by eye. And some people have the talent to spot these things, and some people don't. But I guess I have that talent. But using computer software, of course, is going to be much better. At least that's what you would assume. But the problem of finding these duplications by software was actually a pretty hard uh, task to succeed in. And I've worked with DARPA to try to crack the code, and there were several groups working on in computer science who could not possibly write software in a week, the small week that the challenge has yeah, to fulfill the task. But in the years after that, several groups tried to work on software finding it, and some of these people have succeeded. So I'm currently using a software tool called Image Twin. It is partially based on artificial intelligence, and another pretty similar tool that also is based on AI is Proofik. So I'm using these two. I'm occasionally using FigCheck and Forensically, which both are free. Each of these software tools has their own strengths and weaknesses, but it is a big step forward, especially because Image Twin also has a database of scanned figures from open access journals, and so you can scan a figure or even a paper against that database, and sometimes it will find very surprising cases of reuse of images across papers. But unfortunately, AI is not always the answer. AI can also create fake text, as we have seen. And so there's, of course, a lot of talk about it because it's a new development that science and also academia is not quite ready for. It now becomes very easy to write an essay, not yourself, but have some chat box deliver your essay written for you in seconds. And so, how do we deal with that as scientists? Should we embrace this? Should we accept this? Should we refuse it? And I think the technology is so new, and the ethical questions surrounding it are so big that we haven't quite figured out yet how to deal with this. And in a way, you could say it's maybe similar to having calculators in the classroom. Is that allowed or not? But this is a little bit more scary because AI cannot just create a correct answer. It can also create fake answers that look very reliable, and it will say it with confidence. But as an example for the weird things that it could generate, is if you read this article, there's a funny little story in which a chat box, BioGPT, was asked to tell how many ghosts there were in U.S. hospitals, and it said, "Oh, the average U.S. hospital has 1.4 ghosts, and the ghosts are very annoying because the patients in these hospitals cannot really heal because the ghosts go through the wards and they disturb the healing of the patients." And you're like, where did this come from? That's not, you know, ghosts don't exist, at least in my opinion, and they should not exist in hospitals. And where did that statement come from? So it also has been found that some of these AI bots can generate fake references, um, and so it can be helpful. But how do we deal with this? And we're not quite ready for this yet. And these will be long discussions between a lot of people in scientific publishing, trying to figure out how can we detect fake AI written text. Can we allow people who are, for example, for whom English is not their first language, it can be very helpful to write a text and then have uh, the Chat GPT or so improve the text to make the English better. And yeah, it's just yeah a difficult topic, but I do want to point it out because not only can AI generate fake text, it can also generate fake images. You might be familiar with some of the images here on the left. these images, these photos look quite realistic, but they are of people we know, but they're showing events that never happened. And maybe Trump gets arrested here in these photos, and the Pope might be wearing a designer jacket. But you can also see that these photos can be fun to look at. We can laugh at them, but they can also, of course, be used to create fake stories that did not happen. And given how good most people are, I'm actually very bad, but most people are good in facial recognition. We can recognize the people in these photos. We can still spot some errors in these photos, but next year the technology will be so good that we can no longer distinguish a fake AI generated image from a real photo. And it's probably much easier to generate a photo of a cell or a Western blot or a gel or so, because yeah, we're not really wired to recognize a gel as real or not. We can see a face, and we can see the nose is at the wrong place, or a hand has 5 fingers or 6 fingers, or yeah, we can recognize which hand looks believable. But these photos could already look believable, and this is a photo generated about a year ago. I think by now the technology is so good that we can no longer distinguish a fake scientific photo from a real scientific photos. And how do we deal with that? I don't have the answer, but I think it's something we need to think about. And then finally, there are, in the hands of the wrong people, this technology can be used to do very bad things. So the problem of paper mills is one that you might have heard about. So paper mills are similar to assay mills. They're networks of people who generate fake scientific papers, um, and they do it for profit. They sell the papers to authors who need papers. We all need papers. If we all need to publish papers in the race that is called science. We need papers for our careers. But in some countries or in some environments or universities, the rules are a little bit stricter than in other places. For example, if you are a medical doctor in certain countries, you have to publish a scientific paper, even though medical doctors in general are not always interested in science, and they're also not given time to do scientific research, but they still have to publish a scientific paper. So it's an impossible requirement. And in those situations, those countries, people might actually see advertisements for scientific paper, for authorships on scientific papers. And so they might decide, and you cannot really blame them, if I invest a couple of $1,000, I will have a scientific paper, and I can move on with my career, and I can become a doctor in a hospital. This is what I wanted. And so these advertisements are pretty easy to find on Facebook or so, and they sell authorships either on accepted papers or on fake papers. And there's different people selling different things. They're scams because the papers are fake. And there's many people like me who work on this problem. And the problems of paper mills that have generated, we believe, tens of thousands of papers that are fake, maybe even hundreds of thousands of papers that are completely fake. It has not been recognized by the scientific publishers. It was recognized by several individuals, and some of these names are mentioned here. In particular, I want to mention Smat Clyde, who has done a ton of work finding one fake paper after another. But many people are involved in finding these papers, and most of these are not even working in scientific publishing, or at least it's not their responsibility. It was recognized by the work of many volunteers who, independently of each other, have worked on this problem. And now scientific publishers are realizing that they had perhaps not paid attention a lot, and they are finding these papers and they're retracting them en masse. So, just as an example, here's what we call the tadpole paper mill. These here are two photos, two figures from two different papers, two different sets of authors who are not related to each other, different institutions. But the background of these Western blots is first of all, it's exactly the same between the different blots in this figure, but also uh, highly similar across different papers. And so there's the particular line here that you can see. So the backgrounds were all the same. And we believe these images are generated with some primitive form of AI in which randomly generated bands are put on the same background. And of course, then we could catch them, but now the crooks have upped their game a little bit, and so now they have actually random backgrounds, so we can no longer really catch them. But this was one of the examples in which we found a set of 600 papers that all used the same blot background. Here's an example of a paper mill, probably a very different set of organizers or fraudsters behind the scenes. So they had, I call this the Iranian plants paper mill. So it's a bunch of papers that all report on plants found in different regions of Iran. And so they sampled plants and did some genetic work on them. If you look carefully at the position where these plants were sampled, the latitude and the longitude, if you know your latitudes and longitudes, you might spot that these are what is it, minutes and hours, minutes and seconds. That the second cannot be 93. That should 59 is the highest second that you can have, but you can see that several of these values have uh, impossible locations. This is not a real location. But not only that, if you then search for these impossible latitudes and longitudes, I found several other papers that had the exact same things. And so here's a bunch of them where these are all different authors, different groups of people, although they had some authors in common. They were all reporting on different plants, so it's hard to read, but they all had these same locations marked in red, and it was just all copied pasted from each other, and it's just weird. So it seems to be that this is a group of authors who were selling fake papers. They were replacing one plant name with another. They were changing a couple of graphs, but a lot of the graphs also were very similar. So it's a bunch of, I think, about 30 papers that had all these impossible coordinates and duplicated values. And so this is clearly generated all by the same studio and sold to authors who need them. Here's another example of a paper mill that works with synonymizing text. So what it does, it will take a text or a paper that has been published, and it will synonymize. So it will find a synonym for every word or expression in the text. And it becomes a little bit funny, these texts. So there's a preprint analyzing this type of writing style, which is called tortured phrases. I'm not a big fan of that name, but it creates these weird sentences that you read and you're like, what does it mean? And so this is a paper that got, I think it's retracted, and you can read chest peril tends to one of the diseases that makes a huge amount of passings dependable. And so it's English, but what does it mean? It doesn't seem to mean anything. And it's basic parts of ladies' ruins worldwide. And then you realize, wait, chest peril is breast cancer. And basic parts of ladies' ruins worldwide means it's one of the main reasons for women's death globally. And if you sort of back translate it, reverse translate it, you might actually find an original text. And so we believe these papers take real papers, they plagiarize it, but they try to hide it, and it becomes a funny, tortured phrases. And so bosom malignancy or chest peril is it just means breast cancer. And then another funny example, there was a paper about bird identification, but the word bird was not used. It was always winged animal. And so it becomes funny. But in reality, this is plagiarized text, but it's hard to catch using traditional plagiarize detector tools. So finally, this is my last slide. So I've talked a lot about, my belief that science is about finding the truth. And I've shown you lots of examples of errors and potential misconduct in science papers. And you can think about how can we tackle the problem of science misconduct, I think we put too much pressure on people nowadays to publish papers, to hold them accountable for the number of papers, the number of citations, the impact factors, and those are all decent measures to measure a person's productivity, but it's maybe we should focus a little bit less on quantification and more on either quality or reproducibility. And we need to slow down science a little bit. We need to perhaps focus on, if you publish a paper, can we reproduce it? But it takes the role of a lot of people who are involved, not just the authors and the reviewers, the journals, the institutions, the funders. There's lots of people who play a role, and we need people to take a harder stance against misconduct and also to have better quality control up front. Peer review clearly is not designed to catch fraud, and as papers get more complex, the discussions on whether a paper is good or not, or what parts of a paper should be improved, becomes also more complex. We need a faster correction and just in general a harder stance against misconduct, because it seems that if the rewards are high, you publish a paper and you have beautiful results, it's just easier to publish, and the chance of getting caught is pretty low. Nobody seems to really care about it. Then you get the situation where people will just cheat, and it would be like having no rules in traffic. If we could all speed and run red lights and just would not have a chance of getting a ticket, I think there would be much more speeding and running red lights in traffic. We need to have some consequences for people who break the rules. And then finally, there's a tremendous cost of science misconduct. There's not just people trying to reproduce papers that are falsified or that contain fatal errors, but also for science as a whole. We've seen in the past couple of years that there has been a lot of people have lost their faith in science. A lot of people no longer believe that climate change is real or that vaccines work. And the story about science misconduct, could be seen in that light. You could walk away from my talk thinking that all science is flawed and that we should just not trust science at all, period. And I hope that is not the message of my talk. I hope that the message is that, yes, there are errors and misconduct in science, but most science is good. Like, I still put all my money on science. We need science to solve a lot of the problems we are facing in the world, like climate change and pollution and pandemics. But we need that science to be good. We need that science to be a little bit more reliable and trustworthy. And I hope that I play my part in doing just that. And with that, you can follow me on Twitter, as long as it's still there, or X as it's called now, Microbiome Digest. And I play the game Image Forensics. It's not really a game, but it's meant to teach people to spot these duplications. And the winner will win an emoji award. So with that, thank you, and I will hand it back over to the panel.
Well, thank you so much, Elisabeth. That was an excellent presentation and really a fascinating insight into your important work. So we do have some questions coming in from the audience. If anyone else has a question, please feel free to post it into the question box at the top right of your screen. So, Elisabeth, first of all, how do you decide which papers you're going to investigate? I mean, do you focus on high impact journals only, or do you spread across the, and how do you go about making that decision? You've done so many.
Um, uh, so in the beginning, when I did that initial search of 20,000, I did a more systematic. So I just said, okay, let's look at plus one. Let's take a journal and just open all papers that have the term Western blot in them and just scan them. And but for every paper that I found that had a problem, you could also say, well, if that lab produced a paper with a problem, it might be worth looking at more papers from that group. So I'm still following up on leads from that period, because I have 800 papers and 800 leads, so that's already a lot.
Mm.
But I also get a daily stream of requests, either through Twitter, email, LinkedIn, whatever, where people ask me, "Can you look at a paper? I think there's something wrong with it. I spotted a duplication, or I think this lab is very unreliable, and you should check out their paper." So I get a daily stream, and I some days it's just too much. Like I cannot possibly follow up on all of these papers.
Mm, mm. Okay, thank you. So, a question from Ezra, who is also from the Netherlands. Ezra says, do you think institutions should have an internal misconduct detection system as a way to ensure scientific integrity and use this before PIs submit their manuscripts to journals? And is this feasible?
Um, it's very tough because there are many ways to do misconduct that would not be detectable by any method. And you could even think of it yourself, not to put any ideas in people's head, of course. I do think some quality control would be good. But as a person who has submitted papers yourself, if you had that extra hurdle, it would be devastated because you're finally ready. You're okay. You want to hit submit, and if you then have to send it through some internal committee
Hmm.
for review, which will take months or weeks, or I don't know, that will slow down science also. Um, I do think there should be, obviously, we should train people to do good science, but we should also have a lot of focus on how to handle suspicions of misconduct. I feel there's a lot of warning that could go out of that. If you know that people are being caught doing misconduct, I think that there's a lot of other people will think twice before they do it. Um, and I think that's where institutions fall short. They don't seem to investigate these cases very well. They try to handle it indoors and behind closed doors and don't announce the results publicly. So I feel that's where institutions could do much better.
Yeah. Okay. Next question. How can we cite an image reported in other published papers? Okay, so I mean, I guess this comes on to how, the advice you gave on how to report this type of misconduct. Do you just want to follow up on that?
Yeah, I think the question is, I might be wrong. How can you reuse an image?
Oh
Is it
yeah, how
okay
can
to
we,
reuse an image or site?
yeah,
I'm not quite sure, but maybe the
yeah. I
person.
think my understanding was how do they report an image? Oh, but maybe not. Yeah.
Oh, yeah. So, well,
Yeah.
there's so if it's to report a problematic paper that you have spotted in another paper, if that's
Mm,
the question, I would say put it on papier. You can do that anonymously. You have to be sticking to the facts. You cannot you cannot say things like, "Oh, I know the author and I know that they cheated." That's not verifiable. So you can only say this image looks remarkably similar to that image, or this image appears to have duplicated elements with some illustration. That's quite okay. You can do it completely anonymously. There's no IP tracking, so it's very safe to publish your concerns without any repercussions for your own uh,
mm,
career. Um, so that's the way I would recommend. But you can also report it, of course, to the journal. So you can uh, so alerting it on papier has
mm,
the advantage that everybody now knows it or could know about it, and then you can also alert the journal, which will take then hopefully appropriate action. They will then contact the authors, etc.
mm. Okay, so I mean, another obvious question is why are these problems not caught during the peer review process? Because normally there's 2 or 3 reviewers. Why are these not caught then?
Because a lot of so peer review is not set up to detect fraud.
Mm,
As a peer reviewer, you're asked to look at a paper. It's a volunteer job. As scientists, we tend to do it on, I don't know, I usually did it on a Saturday morning or a Friday night. Like it's sort of an extra job you do on top of your regular job. You're not paid for it. So that's already a setting where you cannot perhaps expect a very deep review of all the problems in a paper. But also, if you look at a paper from the point of view that you trust the results and you are just asked to say, could the science, is the science correct? Is the interpretation of the results correct? You look at it from a different way than if what I do is like, could this paper contain an error or fraud? I think that's just a different set of glasses you put on and you look at it from a different angle.
mm. Mm.
Um, but yeah, I feel the real process of fraud detection should be with the publishers because they're the ones making lots of money, and they should have some better quality control, and it should be done by paid people who look at a paper from a very specific angle. Not only could it be fraud, could there be images with problems, but also could there be statistical problems? Could there be ethical concerns? So there's different viewpoints you can take, and that should be done by staff who works at journals.
Mm. Well, actually, yeah, thank you for that. So, in relation to that, Karina asks, are any of the big publishers actually working with you, consulting with you, and implementing checks and changes to the editorial review process? Um, you know, based on on consultation with you.
Yes, so a little bit more so than a couple of years ago. In the beginning, I was considered, I guess, and I couldn't see that, a person who created a lot of work for them, a person who perhaps wasn't responded to. But I think over the years, I've gained more respect, and um, I have done consulting for journals. It doesn't, or publishers, doesn't happen very often. Um, I still like most of my time to do sort of volunteer work, but yes, I have, and I think based on not only my work but that of many other science detectives, scientific publishers have realized, like we have been a little bit too lenient in relying on our peer reviewers. We should. There's many papers that have slipped through the cracks that are probably either paper mills or that are individual cheaters or that have some peer review ring, and so you can now see that papers are being retract in massive amounts, like hundreds of papers at the same time are
Mm.
retracted from journals nowadays. And yeah, so journals have learned from what we're doing and are improving their guidelines based on the work that we do.
Hmm. So, I mean, so why, going back to that pie graph that you showed, where you had the huge blue section where no action is taken. I mean, you mentioned some of the reasons, but why is it taking journals so long to act on these? I mean, I can imagine if you submit a list of 100 papers to a journal and say these have all got problems, they've got to find the staff to have to, to go and
Yes.
deal with this. But anyway, carry on.
Yeah, so in particular, plus one, I had a glimpse behind the scenes. So I did report half of the 20,000 papers that are screened, roughly half of them were from plus one, just because it was an easy journal to flip through. So not because I had any suspicions against plus one. But yeah, I did send them an email saying, here are 350 papers from your journals with problems. And so it was just overwhelming for them. And they had to hire a couple of people to go through this stack. And they're still going, 5, 7 years later, they're still going through the stack that I sent them back then. Um, so that's one reason. It's just probably overwhelming, just dealing with the backlog that they just had not noticed. Um, but also contacting authors is much harder than you think. It's a lot of people move on in academia, so their email addresses of the corresponding author do not work. If the corresponding author doesn't answer, what are the email addresses from the other authors? Usually only one email address is given. If that bounces or if that is not responded to, then a journal doesn't really know what to do. And they have the power to retract the paper even if the author didn't reply. But I think a lot of journals want to do it the right way, want to give the authors a chance to respond. And then maybe they also alert the institutions who might or might not respond. And then there might be an investigation, which can take years if it's an institutional investigation. And there's many, if you wait for all these steps to happen, that can take years.
Hmm.
So, and then sometimes there's even authors who threaten to sue the editor. And I think being threatened to be sued is actually, I mean, I've had a couple of those letters. It's very threatening. And yeah, you can imagine that an editor is like, well, I guess then I'm not going to retract the paper. But yeah, there have been a couple of cases
Hmm.
where that happens.
Okay, well, thank you. So I think we've just got time for one final question, Elizabeth. So, obviously you mentioned the editors might receive threatening letters, but what about you? I mean, do you receive any personal pushback or harassment because of the important work that you do?
Yes, I have. I get a daily stream of nasty messages on Twitter from fans of particular authors whose work I've criticized. I've gotten some not too bad, but yeah, I got some nasty emails, and I got some legal threats. So I got a couple of times. I got a letter where authors of a paper said, "Oh, we want you to remove your blog post, or we want you to remove your tweets, or else dot dot dot." And I'm not quite sure what the or else is. So in those cases, I decided to not uh, to take down one tweet that was years old, and but I also wrote them back. Nah, I'm not gonna remove anything else. So sorry. And then I didn't hear anything back. So a lot of these letters are threats. But I have one legal complaint filed against me in France. I haven't heard anything of that. I was, written up for harassment of the author. But yeah, to the best of my knowledge, I am not in serious legal trouble in France. I've actually been in France and I was not arrested, so I think I'm good. But yeah, at some point there will be a legal threat where I'm, I might be sued. There's actually now one that the the woman at Harvard who has been accused of misconduct is now suing the people who wrote reports on data colada about her work and concluded that some of this looked like it might have been fraud. She's suing for defamation, and it's a $25 million lawsuit. And so I think if you are a volunteer like me, that is overwhelming, and I'm not quite sure how I would deal with that.
Mm, mm. Okay, well, Elisabeth, thank you so much. That brings us to the end of today's webinar. Thanks again for for your insightful presentation and a great discussion. And also thank you to the audience for taking the time to attend today and listen in. So until next time, good luck in your research and goodbye from all of us at Bite Size Bio.
Great. Thank you for having me on. Bye, Em.